Bit. A bit is the smallest unit of digital information and the foundation of everything in the digital world. The word bit comes from binary digit, which means it can have only two possible values, 0 or 1. You can think of a bit like a light switch that is either on or off. Computers do not understand words, images, or sounds the way humans do. Instead, they process and store information using long sequences of bits made up entirely of zeros and ones. On its own, a single bit carries almost no meaningful information. It simply represents a basic yes or no choice. However, when bits are combined, they become powerful. For example, 8 bits form 1 byte, which is enough to represent a single character, such as a letter or a number. By grouping millions or even billions of bits together, computers can store photos, play music, stream videos, and run complex software. Every action you take on a digital device, typing a message, opening an app, or watching a movie is ultimately translated into bits. In this sense, bits are the building blocks of all digital data. Understanding what a bit is helps you understand how computers think, how data is stored, and how the entire digital world operates at its most basic level, byte. A byte is the next step up from a bit and is one of the most important units in digital storage. While a single bit can only represent a 0 or a 1, a byte is made up of 8 bits working together. This combination allows a byte to store much more meaningful information. In most computer systems, 1 byte represents a single character, such as a letter, number, or symbol. For example, the letter A. The number 7 or the symbol is typically stored as 1 byte. To understand the difference clearly, imagine a bit as a yes or no question. While a byte is a full answer, a bit can only say yes or no, but a byte can choose from 256 different values. That is why text, basic data, and simple instructions are measured in bytes, not bits. A short text file might be only a few kilobytes, but at its core, it is still made up of thousands of individual bytes. In real life, bytes help us understand file sizes. A single plain text page may use a few kilobytes, while an image can take up millions of bytes. Compared to a byte is far more useful and practical, making it the basic unit of storage that computers rely on to represent information in a way humans can actually use. Kilobyte. A kilobyte is like a small paragraph instead of a single letter in the digital world. If a byte is 1 character, 1 letter on a page, then a kilobyte is a short note made of many letters put together. Technically, 1 kilobyte equals 1024 bytes, because computers count using binary rather than the base 10 system humans use. This means a kilobyte can hold hundreds of characters, enough for a short message or a simple document. Think of a kilobyte as a sticky note compared to a byte being a single letter written on it. A sticky note isn't huge, but it's big enough to carry useful information, small text files, simple emails without attachments, and basic web pages often fit neatly into a few kilobytes. In the early days of computing, having a kilobyte of storage felt impressive, like having an entire notebook instead of just 1 page. Today, kilobytes may seem tiny, but they're still everywhere. Every menu text, setting file, and lightweight piece of data relies on kilobytes. Compared to a byte, a kilobyte is the first step where data starts to feel human-readable, acting as the bridge between single characters and larger files like images or music. Megabyte. A megabyte is where digital data starts to feel substantial. If a kilobyte is like a short note, then a megabyte is more like a full page with images. Technically, 1 megabyte equals 1024 kilobytes, which means it contains over 1 million bytes working together. That amount of data is enough to store real content, not just text, but also photos, audio, and small applications. To picture it more clearly, imagine a megabyte as a thin magazine page instead of a sticky note. A single high-quality photo taken on a smartphone often takes up a few megabytes. An MP3 song might be around 3 to 5 megabytes, and a short PDF document with images can easily reach several megabytes. At this level, data becomes something you can see, hear, and interact with in a meaningful way. Megabytes are also where file sizes start to matter in everyday life. When you download an app, send a photo, or attach a file to an email, you are usually dealing with megabytes. Compared to kilobytes, a megabyte represents a huge jump in capacity, marking the point where digital storage moves beyond simple information and into rich, media-filled content. Gigabyte. A gigabyte is a large unit of digital storage that we use every day. If a megabyte is like a single photo or a short song, then a gigabyte is like a whole photo album or a playlist. Technically, a 1 gigabyte equals 10 0.24 megabytes, which means a huge amount of data combined together. At this level, storage is no longer about small files, but about collections of content. To make it easy to imagine, 1 gigabyte can hold hundreds of photos, dozens of songs, or several short videos. A full HD movie usually takes a few gigabytes, and many smartphone apps today are also measured in gigabytes. This is why phone storage options like 64 GB, 128 GB, or 256 GB matter so much, they decide how much content you can keep without running out of space. Gigabytes are everywhere in daily life. Your internet data plan, your laptop storage, and your USB drive are all measured in gigabytes. Compared to megabytes, a gigabyte is a big step up, marking the point where digital storage becomes powerful enough to hold videos, games, and large apps comfortably. Terabyte. At the terabyte level, storage stops being about single files and starts feeling like a personal archive. This is the kind of space where years of digital life can live in one place. Technically, 1 terabyte equals 0.24 gigabytes, but numbers don't fully capture what that really means in practice. Think about everything you create and collect over time. Photos from different phones, videos from trips, work files, backups, music, and movies. All of that can quietly fit inside a single terabyte. A photographer might fill a terabyte with raw images. A video editor can use it up with just a few high-quality projects. For most people, a 1 terabyte drive feels like I don't need to worry about storage anymore. Terabytes are where storage becomes long-term. They are used for hard drives, backups, and personal data vaults. Compared to gigabytes, a terabyte isn't just bigger. It represents ownership of data over time, a place where your digital history can safely accumulate. Petabyte. A petabyte is the point where data becomes too large to imagine as personal storage. This is no longer about one person's files or even one powerful computer. 1 petabyte equals 1.024 terabytes. But more importantly, it represents data at an industrial scale. At this level, storage belongs to organizations, platforms, and entire systems. Instead of thinking about photos or videos, think about activity. Every click, search, upload, message, and stream creates data. When millions of people do this at the same time, every day, that information quickly grows into petabytes. Large companies use petabytes to store user data, logs, backups, and content libraries. A single video platform can process petabytes of data without you ever noticing it. Petabytes live inside data centers, spread across thousands of servers working together. They are invisible to everyday users, but they quietly power the services we rely on. Compared to terabytes, a petabyte is not just more storage. It marks the shift from personal data to collective, global-scale data. Exabyte. An exabyte is the moment when data becomes too big to belong to any single place. It's no longer about servers, buildings, or even companies. At this scale, data behaves more like a global atmosphere constantly moving, growing, and surrounding everything connected to the internet. Technically, 1 exabyte equals 1.024 petabytes, but numbers stop being helpful here. What matters is that exabytes describe data created by billions of people and devices, all active at once. Instead of thinking about files or servers, think about flows, global video streaming, international cloud services, online maps, social networks, and constant backups all generate data every second. When billions of devices are connected, phones, computers, cameras, sensors, their combined output quickly reaches the exabyte level. This is the scale at which the internet itself operates. Exabytes are not stored in one place. They are spread across continents, mirrored in multiple data centers for speed and safety. Most people will never directly own an exabyte of storage, but they interact with exabyte-scale systems every time they scroll, stream, or search. Compared to petabytes, an exabyte represents the transition from large-scale infrastructure to planet-wide digital activity. Zettabyte and Yottabyte. Zettabytes and Yottabytes exist at the edge of what humans can realistically imagine. These units are no longer about storage devices or infrastructure, but about the total scale of human data creation. A zettabyte equals 1.024 exabytes, and a yottabyte equals 1.024 zettabytes. Yet even these definitions feel symbolic rather than practical. Zettabytes are used to describe the amount of data humanity generates over a year. Everything from messages and videos to satellite data, scientific measurements, and machine logs. This is the scale of the global digital footprint, where data is constantly being created faster than it can ever be fully counted. Yottabytes go even further. They exist mostly in theory, representing a future where every object, system, and environment continuously produces data. At this level, data stops being something we store and starts becoming something we manage and interpret. Zettabytes describe the present trajectory of the digital world, while yottabytes hint at a future where information surrounds everything we do. These units remind us that digital growth is not just about bigger numbers, but about how humanity learns to live inside its own data.